This is Mrs. O'Neill for AP Chemistry, Chapter 16, Section 8, the relationship between Ka and Kb. Something should come to mind right now. Aha, that equation Ka times Kb equals Kw, which we also want to remember: the stronger the acid, the weaker its conjugate base. Very important. Now, we've talked about that before, and we're going to bring it to your attention more and more. So pause the video, fill in the blanks, and then play to hear my words. So this should make sense. This you already know. This we've already used. We've already used this equation when we dealt with weak bases. So if we have H plus times OH minus, we can say that that's equal to Kw, or we can say it's that Ka times Kb. So we have a lot of options here to play around with this equation. So do you understand the trend? Please, please, please make sure you're understanding. The stronger the acid, the weaker its conjugate base. So here's an acid. We're going to remove an H plus. We get a conjugate base. That conjugate base is so negligible. In other words, there's hardly any basic properties at all because the acid is so strong, and that's why we can say really the base doesn't exist. But if you come down here a little bit, here we have what's called a weak acid. And I'm going to bring this to your attention because if we have a weak acid and a weak conjugate base, this is going to do a lot for us when we talk about buffers. So notice those numbers. Notice those Ka and Kb numbers. They're very close to each other. And because of that, it's going to make for a nice, good buffer. Okay, now if you get even farther down to something like this, we have something like this as a strong base, O negative 2, well then the acid, which should make sense here, OH negative, there's not going to be any acidic properties in OH negative. For crying out loud, that's a base property, right? A really, really strong base property, right? So when we have a strong base that is in water and it dissociates into OH minus, it is purely a base because we have all of those OH minus in solution. So hopefully this makes sense. Stronger the acid, weaker conjugate base. Same thing down here. The stronger the base, the weaker the conjugate acid. So we want to kind of keep that in mind. And our Kas and Kbs are going to help us decide which way that is. So what does P mean? Well, P basically means the negative log. So we're going to talk about pKas and pKbs because we're going to talk about this when we are dealing with the titration curve. Okay, this is going to help us with that titration curve, which you're going to learn in great detail next chapter. So pKa equals the negative log of Ka, pKb equals the negative log of Kb. That should make sense. And we also want to remember that the pKw is 14, but at 25 degrees Celsius. Remember, our equilibrium constants can change depending on the temperature. So we want to keep that in mind as well. So pause the video, give this some thought. Can you calculate the value of pKa for our HF, which is down here? This is our Ka value, and our pKb for the F minus, which again the value is down here. So pause the video, see if you can take the negative log of those to make sure that we're understanding how to do that. And you should have gotten 3.17 and 10.83. So this should make sense. Our HF is acidic, so it should be less than 7, which it is. And our F minus is basic, so it's going to be greater than 7. Okay, see you later.